So as we seen earlier, this deformation is represented in the units of length. Okay. So now, as we see this strain is nothing but this deformation in the bar per unit length of the bar. Okay, just take this way. For example, there is a rod over here. The length is something like 100 mm, a small bar. So because of the tensile forces, what happened is the size of bar has been increased a bit. So this is the original length, right? This is the 100 mm, and because of that force, tensile force, it has increased it by a length of 10 mm. Okay, of course, we know delta L is equals to change in length equals to 100 mm. This is the deformation, right? But this 10 mm is the change in length for what? For 100 mm length of the bar. Okay, but what we are doing is we are trying to represent this change in length per unit length. Ante 100 mm ki inta change aithe. If 10 mm is the change in length for 100 mm original length, what will be the change in length for 1 mm? What is going to be the change in length if the bar is 1 mm? Or if 10 mm is the change in length for the 100 mm original bar, how much do you think 1 mm of section has been elongated? I hope you understand here. Okay, ikkada 10 mm ante enti, that is the increase in length for 100 mm length of bar. ఓకే, కానీ ఇక్కడ మనం ఏ విధంగా రిప్రజెంటేషన్ చేస్తామంటే ఈ ఇంక్రీజ్ ఇన్ లెంత్ అని. సో ఇక్కడ 100 mm-కి 10 mm ఇంక్రీజ్ ఇన్ లెంత్ కదా. సో నేను ఒక చిన్న స్ట్రిప్ తీసుకుంటా, ఇక్కడ చిన్నది హూస్ విడ్త్ ఈస్ 1 mm. ఈ 1 mm లో 1 mm లెంత్ ఆఫ్ బార్లో ఎంత చేంజ్ ఇన్ లెంత్ వచ్చింది ఎలా తెలుస్తుందండి? టోటల్ ఇంక్రీజ్ ఇన్ లెంత్ డివైడెడ్ బై ఒరిజినల్ లెంత్ ఆర్ టోటల్ లెంత్ ఆఫ్ బార్. అంతే కదా, ఇందాక అనుకున్నట్టుగానే మనం పెన్స్ గురించి మాట్లాడినట్టు దెర్ ఇస్ ఎ ప్యాకెట్ ఆఫ్ పెన్స్ లాగా. ఓకే, సో ఇక్కడ కూడా ఏం చేస్తాం అంటే దిస్ ఈస్ ది టోటల్ కాస్ట్ ఆఫ్ పెన్. ఓకే, దిస్ ఈస్ ది నెంబర్ ఆఫ్ పెన్స్. సో టోటల్ కాస్ట్ డివైడెడ్ బై నెంబర్ ఆఫ్ పెన్స్ will give the cost of each pen. Atlane, if this is the total elongation and this is the original length of the bar, this 10 divided by 100 will give the change in length for 1 mm of length. That is why we use here per unit length of bar. Okay, I hope you understood here. So representing that, how deformation per unit length is nothing but strain. We call this as strain. Okay, so now you understood what is meant by strain. Strain is defined as deformation per unit original length. Strain has no units because strain is nothing but deformation of original length. Both has the same units. Therefore, this parameter has no units. Okay, now let us see the types of strains in a body. The first one is tensile strain, which is denoted by epsilon T. Compressive strain, epsilon c, and also shear strain epsilon t. So we have three types of strains here. So now coming into this strain. So as we see, strain is nothing but change in length by torsional length, and that change in length is because of the externally applied load or stress. Okay, so now if the change in length or if the strain is because of the tensile force, then such a strain is called as tensile strain. And if the strain is because of compressive force or compressive stress, then such a strain is called as compressive strain. And if the force which is responsible for the strain is shear force, then such a strain is called as a shear strain. So let me go into a little bit explanation here. So let us take a bar here over here. See, the dark line here mentions denotes the original length, whereas the dotted diagram indicates the changed or the final length of the bar after elongation. So as you can see, this is the tensile force acting. So because of this tensile force, the length is going to be increased. Okay, but here you need to understand two things. Okay, this bar has length L and width of B. Okay, so this bar has two dimensions. Of course, this is a square cross section, therefore he mentioned only B. So if this is B, this is also B. Okay, so now this L is nothing but longitudinal dimension of that bar. Longitudinal, L-O-N-G-A-T-U-D-I-N-L, longitudinal dimension, whereas B is equals to lateral. Okay, you understand? This length is called as longitudinal dimension, and this B is known as lateral dimension. So what is happening to these two dimensions? Okay, so now as the tensile force is being applied, the longitudinal dimension L is going to increase. But what happens to the lateral dimension B? Actually, the lateral dimension is going to decrease. Okay, remember that. When the longitudinal dimension is increasing because of tensile force, the lateral dimension is going to decrease. This is what happens in your an elastic material like rubber. Take into your hands a rubber band. If you see, the cross section will be of square, right? If you elongate that by stretching with both your hands, what happens is it is going to become thinner and thinner at this section center. If you have seen, you can notice that. Okay, so what is happening here is because of this tensile forces applied here, this length is going to increase, but even though there is no force acting on this side and this side, the lateral dimension is also going to change. Okay, how it is going to change? It is going to decrease. And the complete opposite thing is seen in this second figure, in the compressive strain. When a compressive force is applied over here, as you can see, this is the dotted line, this is the final shape. Initial shape, this is the initial shape, and after applying force it has been shrink, it has been shortened. What happened is the longitudinal dimension has been decreased, whereas you can see the dotted lines, the final lateral dimension has been increased. So the deformation in these tensile forces and these compressive forces are quite opposite to each other, isn't it? So the thing that you need to remember is, even though force is not acting in this direction, there is a lateral strain. Lateral dimension is also going to change. Therefore, in a given body, you are going to have two types of strains. Okay, of course, tensile strain, compressive strain, and shear strain the different types of strains are classified based on the type of stress or type of force that is responsible for such strains. But here the longitudinal and lateral strains are classified based upon the direction in which that strain is taking place, or the deformation direction, or which dimension is being changed. Okay, so now as you can see here in this first diagram, first figure, let me just clear this for once. Now as you can see in this figure, so delta L by L, change in longitudinal length divided by its original length, will give E, which is called as longitudinal strain. Okay, this is what we call as longitudinal strain. But here you can also write delta B divided by B, which is called as E, but it is lateral strain. Okay, so we have longitudinal strain and lateral strain depending upon the deformation or the dimension which is deforming. Okay, so this is the classification made based on the dimension which is being deformed. Okay, if the deformation is in lateral direction, that is called as lateral dimension. If it is seen in the longitudinal direction, that strain which we got in the longitudinal direction is called as longitudinal strain. Okay, so this is what is about tensile strain and compressive strain and longitudinal and lateral strain. Let us see the shear strain. Shear strain is represented with epsilon t. So this is a bit different from previous strains. Okay, so how is it different? It is different because in the previous case, the tensile forces and compressive forces are acting normal to the surface. These are perpendicular to the surface here. This angle is 90 degrees, right? But so if you see this figure over here, the force is acting in this direction, right, parallel to the surface. So to understand this shear strain, let us consider this body over here. Okay, so this is the original body, rectangular body, which is just fixed, okay, at the bottom, and now a shear force F is acting on the top surface parallel to it. So what happens is, since it is fixed at the bottom, it will not get displaced. It will not go from one place to another, right? But it is going to distort, right? It is going to bend forward. Okay, try to push some pole. See, for example, take a pole. Okay, a small pole which is fixed in the ground. Okay, and other end is free in a like this. And if you try to push the body with your hands, what happens is the pole is not going to move, but it is going to deflect, right, in this manner. So this is the new shape of that body. Because of that force, the body has taken this shape, isn't it? So this is the original shape, and this has been the final shape. So this has been undergone strain for sure, right? So the angle present here is denoted with phi. Let us take that as phi. So now this shear strain is nothing but tan of that angle, tan of that phi, tan phi. Okay, so tan of this phi. So what do you mean by tan of phi? Okay, how can I write just simply like this? Shear strain is equals to tan of phi. Okay, so if you see the previous figure here, in order to write compressive strain, what I am doing is I am calculating this delta L and dividing with this length L, isn't it? So if you see in this figure, this is the original side, right? Initial side. But because of the deformation, this side LM has taken the new shape LM dash. Okay, so the deformation which has been undergone here is in terms of angle, not in terms of length. Okay, it has been deformed with an angle. Okay, so here the deformation is not a length, the deformation is nothing but an angle, right? Phi. So tan of that phi gives the shear strain. And the shear strain, as we seen earlier, is denoted by epsilon s, and therefore epsilon s equals to tan phi. But here, this phi is going to be very small. This phi is going to be very small. Just like, for example, let it be like 7, 8, 9, or 10 degrees, even smaller, right? So when that phi is smaller, tan of phi is equals to phi, because phi in radians will be equal to tan of phi when phi is very much smaller అన్నమాట. ఈ కాన్సెప్ట్ మీరు వినే ఉంటారు చాలాసార్లు. Of course, you can verify this statement by calculating yourself in the calculator. Suppose take phi as 5 degrees. Calculate what is the value of tan 5 degrees. Okay, and now convert the 5 degrees in radians. Now compare the phi value in terms of radians and tan phi value. It is almost same, near. Okay, so shear strain is nothing but tan phi, and you can approximate that into 5 radians. Okay, so now let us take an example problem to make you understand how to calculate stress and strain. Okay, this is very simple problem which we are going to discuss here. Okay, so there is a prismatic bar whose cross section is 25 by 50 mm and length of 2 meters. So there is a bar, oka rod unde, and that bar or rod has a cross section of 25 mm by 50 mm. So the cross section is nothing but a rectangular cross section, right? And the length of the bar is 2 meter or 2000 mm. And an axial load is being applied on that bar. How much it is? 90 kilonewton. 90 kilonewton is nothing but 90 into 10 to the power of 3 Newton. Okay, the measured elongation of the bar is 1.5 mm. What do you mean by elongation of the bar? Elongation of the bar is nothing but deformation of the bar. We call it as increase in length as elongation and decrease in length as contraction. Okay, so elongation is nothing but increase in length, deformation. So this is nothing but our delta L, and this is our L. Okay, so multiply these two to get cross-sectional area. Okay, and this is the tangential force. So you can easily calculate the value of stress. Stress equals to force by area. Force 90 kilonewton, 90 into 10 to the power of 3 newtons lo rasanu, and divided by 25 into 50, and this is 50. This is 50. So here the cross section. So 25 into 50. So calculating this will give you this value, 72 Newton per mm square. Okay, so now calculate this strain. So if you see this figure, the length of this is 2000 mm, isn't it? And the increase in length is actually 1.5 mm. So strain is nothing but increase in length divided by original length. This is equals to this value. So what does this value represent? I told you while I am discussing the definition of strain, right? So this is nothing but the change in length, okay, per unit length of that bar. Okay, so if you multiply this again with the total length of the bar 2 meter, what you get is you get the total elongation. Okay, but as you are dividing with the length of the bar, what you are getting is this is the deformation per unit length. Okay, I hope you understood this. So this is a simple example. We are going to solve few more examples, but before going into that, we have another law which we need to discuss here. Okay, that is nothing but Hooke's law. Hooke's law is given by Robert Hooke. Okay, so what does he state is, he stated that within elastic limit, stress is directly proportional to strain. Stress is related to strain. How is it related? Directly. Okay, so it is related directly. I mean, you can say that the stress and the strain are just like best friends up to elastic limit. After elastic limit, these two are not friends at all, are not good friends. Okay, bad friends like. So up to elastic limit, stress and strain are directly proportional. So what do you mean by directly proportional? Okay, what do you mean by stress and strain being directly proportional? It means that if the value of stress changes, the strain is also going to change, but how it is going to change is directly. Okay, stress is proportional to strain. You can see here, right? Directly proportional. So if stress increases, strain increases. If stress decreases, strain also decreases. Okay, and this is going to be linear variation. So if you try to plot a graph over here, this is strain and this is stress. This is how it is going to be, a straight line. This is stress proportional to strain. So as the stress increases, strain also increases. So now in such a case, I can write like this: as stress is directly proportional to strain, as stress is directly proportional to strain, I can write stress divided by strain is nothing but a constant isn't it? So we named that constant as Young's modulus or modulus of elasticity, capital E. So this constant is nothing but modulus E. So remember this: Young's modulus or modulus of elasticity is ratio of stress by strain. So as you see here, the Young's modulus is found using universal testing machine. Of course, there are different ways of measuring the Young's modulus of a material. We can use one of the instruments that we can use in order to find this is universal testing machine. Okay, so the Young's modulus is going to be different for different materials. For different materials, the value is going to be different. The steel or the iron has a different value, and concrete, the most commonly used material, has a different value, and rock, for example, rock stone, it has a different value. But as you see, steel has a value of 200 gigapascal. Okay, remember that this Young's modulus has the same units of stress, because Young's modulus is equals to stress by strain, isn't it? See here, stress by strain, right, equals to stress by strain. Strain has no units there. Therefore, the units of stress is equals to Young's modulus, right? So now, I hope you know this conversion of units, right? It is a simple conversion in which I converted the Newton per meter square into Newton per mm square. Okay, so you know that 200 gigapascal, Pascal is nothing but 1 Newton per meter square, and giga means 10 to the power of 9. So 200 gigapascals is equals to 200 into 10 to the power of 9 Newton per meter square. I'll just split this into this. Now, if you wanted to write it into mm square, this is the simplest way. Okay, so you know 1 meter is equals to 1000 mm, right? So 1 meter equals to 1000 mm. Now square it on both sides. What you find is 1 meter square is equals to 1000 square, and 1000 10 to the power of 6, right? 6 mm square. So put this. What happens is 200 into 10 to the power of 3 into 10 to the power of 6 Newton divided by 10 to the power of 6 mm square. This 10 to the power of 6 and this 10 to the power of 6 will get cancelled, and what remains is 200 into 10 to the power of 3 Newton per mm square. So this is the easiest way of converting units. And once again, E is equals to compressive stress or tensile stress divided by strain, and this is what we use. And sometimes we use this suffix to indicate what is the force and what is the nature of force that is responsible for that stress. Okay. Similar to elastic modulus E, there are two more properties that a material has, such as rigidity modulus or modulus of elasticity. Modulus of rigidity, and the other one is bulk modulus or volume modulus of elasticity. So let me briefly explain you about these two parameters also. Modulus of rigidity or rigidity modulus is denoted by C or N or G. It is defined as ratio of shear stress and shear strain. As you know, E is equals to tensile stress by tensile strain or compressive stress by compressive stress. But here, modulus of rigidity or rigidity modulus is nothing but shear stress divided by shear strain. Okay. So now this is also called as shear modulus because it is the ratio of shear stress. Okay, shear modulus of elasticity. Okay, so it is same units. You have the same units, right? Stress by strain. Strain has no units, so C has the units of stress. Okay, coming to the third one. See here, bulk modulus is defined as the ratio of normal stress on a body to volumetric strain. The formula is the same, stress by strain, but what is different here is the bulk modulus is defined as the ratio of normal stress divided by volumetric strain. It is the ratio of normal stress and volumetric strain. Okay, so that is why we have three modulus. Okay, Young's modulus, bulk modulus, and rigidity modulus, because the stresses are not the same. Okay, so now what do you mean by normal stress and volumetric strain? Volumetric strain in this is the change in volume. Okay, if you take a two-dimensional body which has a length and a width, and if you elongate, it is going to elongate only in the two direction. So you are going to see the change in longitudinal direction and lateral direction. But if a stress is being applied on a body on the three directions also of the body, then each and every dimension is going to change, and the summation of strain in each direction gives the volumetric strain. To understand this, let me take this body. So let me take this body. So this is nothing but a cuboid, and this is the coordinate axis, right? This is the length, B width, and this is D. Let it be X, Y, Z. So when a force is acting on this direction and in this direction, you are going to have change in length of the body L. Therefore, you are going to have EX. EX is nothing but strain in the body in the direction of X. Okay. And next, if a force is acting in the direction of Y, the change is going to be seen in the width of this body, right? B. Therefore, in which direction it is going to be? y. It is going to be in the direction of y. Therefore, the strain is represented as Ey. And similarly, if there is a force from top and bottom acting on this body, we are going to see Ez. So, summation of all these three will give us the volumetric strain. Okay. Uh, as you see in this figure, I have taken all the compressive forces, right? If I take this and this as compressive and I take this as tensile force, the sign of this value changes. Okay, because if these are increasing, this dimension is going to increase when these two dimensions are going to decrease, right? So this convention you will understand further as we go. We are going to solve some problems also calculating the volumetric strain and all. Okay, you get a clear idea about that there. So this is what is volumetric strain. What is normal stress? Normal stress is the stress that is caused because of this normal forces. See here, each and every force is acting perpendicular to this area, right, at 90 degrees. So when a force is acting at a 90 degrees to a surface, to an area, that force is called as a normal force. So the stress because of that normal force is called as normal stress. Okay, so with this I am concluding the elastic moduli. Okay, plural word, moduli. So we have three: Young's modulus, bulk modulus, and rigidity modulus. Okay, so let me just remind you about this formula over here. Young's modulus, stress by strain. Stress is force by area, and strain is epsilon. Of course, epsilon can be written as delta L by L. Of course, this is delta L. Okay, this is small delta, which looks like somewhat S, right? So P by A divided by delta L by L, and just reshuffle these terms. So delta L it will be equals to P by A into L by E. So what is delta L? Change in length. So by using this expression, you can find out what is the change in length in a bar. Okay, in any bar. If some load is acting on a bar, you can calculate it, either tensile force or compressive force. Okay, so remember this equation. And also you can write this way. See here, strain is equals to, from this expression I am writing, stress divided by E. We are also going to use this expression in solving the problems. Okay, you need to get habituated with these equations. You have to practice them and remember them so that you can solve the problems easily. Okay, so therefore we have discussed these three, okay, in this class. So now let's see what is the relation among the following. Each and every moduli is related. Okay, each and every one is related to each other. So let us see what is the relation between E and C, and also let us see what is the relation between E and K. Okay, that gives the relation between these three terms. Of course, we have certain final equations which we got, but let us see how those relations are also derived. Okay.